the enigma of quantum linking. Though it may sound almost magical, quantum linking, commonly referred to as entanglement, is one of the most experimentally supported and fascinating concepts in the realm of quantum physics. It presents a challenge to our current comprehension of the fabric of space, time, and reality itself. The origins of quantum linking can be traced back to the formative years of quantum theory in the early 1900s. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen introduced a conceptual scenario that came to be known as the EPR paradox, Einstein-Podolsky-Rosen paradox. At that time, Einstein remained doubtful about quantum mechanics. He struggled to reconcile its intrinsic unpredictability and indeterminacy with his vision of a structured and deterministic cosmos. Einstein and his peers argued that if quantum mechanics were to be believed, it would mean there existed peculiar, non-local connections between particles. That is, two particles could be so deeply connected that the state of one could instantaneously determine the state of the other, even if separated by vast distances. They regarded this spooky action at a distance as a sign that something was missing in the quantum framework, some hidden factors that might allow for a classical, deterministic explanation. Fast forward to the 1960s. Irish physicist John Bell took this criticism earnestly. He formulated a theoretical construct, now known as Bell's theorem, which provided a way to test whether quantum predictions or hidden variable theories better matched reality. According to Bell, if quantum mechanics were accurate, it would produce observable statistical discrepancies between entangled particles that classical physics couldn't replicate. Over the decades that followed, numerous experiments were conducted to test Bell's theory. One of the most prominent series of tests was conducted in the 1980s by French physicist Alain Aspect. Each of these trials confirmed the predictions made by quantum theory. Entangled particles really did behave as if they were immediately linked, no matter the distance separating them. These experimental confirmations left no room for classical interpretations, cementing quantum linking as a foundational concept in quantum mechanics. This entanglement represents a distinctive connection between two or more particles, where measuring the state of one immediately determines the condition of the other, regardless of spatial separation. Even if the particles are on opposite ends of the cosmos, this influence remains intact. To make this easier to understand, picture tossing two coins that are quantum linked. Normally, two tossed coins would show unrelated outcomes. One might be heads, while the other is tails. But with quantum linked coins, observing one as heads would automatically result in the other showing tails, as if they exchanged information instantly. Their connection remains firm, regardless of whether they're nearby or across galaxies. In quantum terms, this means that entangled particles, such as photons or electrons, exist in a shared quantum state. Any change to one is reflected in the other. For instance, if two entangled photons are analyzed and one is found to have vertical polarization, the second will immediately exhibit a complementary polarization, even if they're light years apart. This sort of behavior contradicts classical physics, which, following the theory of relativity, tells us that nothing, not even information, can travel faster than light. Yet, entanglement appears to defy that rule, with changes occurring instantaneously. It suggests that space, as we understand it, may be an illusion, or at least not as straightforward as our intuition suggests. This mysterious bond between entangled particles hints at a deeper level of connectivity in the universe, one that surpasses our conventional notions of space and separation. Even though it appears baffling, quantum linking is not just theoretical speculation. It holds practical significance, especially in the rapidly evolving domain of quantum computing. Unlike classical bits, which exist in a binary state of either 0 or 1, quantum bits, qubits, can exist in both states simultaneously, thanks to a phenomenon called superposition. Entanglement allows these qubits to interact in intricate ways, enabling quantum machines to process complex problems much faster than their traditional counterparts under certain conditions. Another practical use is quantum cryptography. Here, entanglement can be harnessed to establish ultra-secure communication lines. If an unauthorized party attempts to intercept entangled particles, the interference will disrupt the entanglement, immediately signaling the intrusion. This has the potential to revolutionize encryption, making data transmission virtually unbreakable. Quantum entanglement also plays a central role in research on quantum teleportation. While this doesn't involve physically moving matter like in science fiction, it does allow for the instantaneous transfer of quantum data between distant points using entangled particles. This advancement could reshape how we handle information over long distances in the future. Beyond its applications, entanglement provokes deep philosophical and scientific contemplation. It challenges our ideas of what space and time are, stretches the limits of what we know, and prompts thoughts on the intrinsic unity of everything. Some theorists suggest that entanglement might point toward a hidden layer beneath our physical reality, an unseen dimension where all things are connected. Yet the nature of this connection remains elusive. Is there an underlying force or principle binding these particles together? Or could it be that space itself, as we perceive it, is not a fundamental component of reality? Quantum linking invites us to grapple with these difficult but fascinating questions and explore possibilities that lie beyond the boundaries of current knowledge. In essence, quantum linking represents one of the most striking revelations of modern physics. Thanks to the pioneering insights of Einstein, Podolsky, Rosen, Bell, and a host of experimental scientists, we've discovered that the quantum domain obeys rules that contrast starkly with classical thinking. Entanglement offers a glimpse into a universe far more unified and complex than we ever imagined, a universe in which particles communicate instantly, regardless of separation. This strange yet beautiful aspect of quantum physics reminds us that our understanding of the cosmos is still evolving. Beneath the visible layers of reality lie secrets waiting to be uncovered, mysteries sparked in the moment of the Big Bang and still unfolding today. Origins of the expanding cosmos. Visualize reversing the entire timeline of the cosmos like rewinding a film reel. Galaxies pulling inward, stars imploding, and vast interstellar clouds of gas and dust compressing into dense clusters. Following this mental journey leads us to a moment when everything in the universe was confined within a tiny, incomprehensibly dense, and extremely hot, singular spot. This idea, known as the expanding universe hypothesis, stands as our most credible scientific account of how everything came into being and developed over time. However, this theory did not emerge suddenly. It was forged over decades through extensive debates, accumulating evidence, and fortuitous breakthroughs. The path toward what we now call the Big Bang concept began with Albert Einstein in the early 1900s. In 1915, Einstein introduced his general theory of relativity, a revolutionary framework for understanding gravity on vast scales. It showed that massive bodies distort the very fabric of space and time. But when Einstein applied these equations to the cosmos as a whole, he encountered a puzzle. His mathematics implied that the universe should either be expanding or contracting, at odds with the prevailing belief that the cosmos was fixed and unmoving. To force a solution that supported a static universe, he inserted a mathematical term called the cosmological constant into his formulas to maintain equilibrium. Around the same time, Belgian scientist and priest Georges Lemaitre found a fascinating implication in Einstein's work. In 1927, he put forward the bold proposition that the universe wasn't fixed, but instead growing. Lemaitre argued that if one reversed this cosmic expansion, all matter and energy would converge to a starting state, a primeval atom, from which the cosmos exploded into being. This idea, daring at the time, was dismissed by many, including Einstein himself. Then came a pivotal moment in the late 1920s. American astronomer Edwin Hubble provided observational proof that would move Lemaitre's idea from speculation to scientifically supported theory. At the Mount Wilson Observatory, Hubble observed distant galaxies and discovered they were all receding from Earth. More surprisingly, the farther away a galaxy was, the faster it was retreating. This relationship, now called Hubble's law, confirmed the expansion of space. These findings suggested that the cosmos isn't stationary, but is stretching, with galaxies moving apart. While this supported a dynamic universe, not everyone was convinced. The scientific community was divided, with many still clinging to the steady-state model. Nevertheless, evidence continued to mount. One of the most convincing discoveries came by chance in the 1960s. Physicists Arno Penzias and Robert Wilson, working at Bell Telephone Laboratories in New Jersey, were testing a large antenna meant for satellite transmissions. They kept encountering an irritating hiss of background noise, seemingly coming from all directions. They tried various fixes, even cleaning bird droppings off the equipment, but nothing eliminated the interference. Unbeknownst to them, Penzias and Wilson had stumbled upon a cosmic breakthrough, the cosmic microwave background, CMB radiation. This faint echo of ancient heat is now understood as the afterglow of the Big Bang, the thermal residue from the universe's blistering birth. The CMB captures the state of the cosmos around 380,000 years after its origin, when temperatures cooled enough for atoms to form and light to travel freely. This detection served as compelling physical proof, the smoking gun, that affirmed the expanding universe model. According to the Big Bang framework, roughly 13.8 billion years ago, the universe erupted from a state of immense temperature and density, often referred to as a singularity. What triggered this expansion remains unknown. Yet, this moment sparked the evolution of everything. In the universe's earliest fractions of a second, it was a turbulent sea of subatomic particles, protons, electrons, and neutrons, too energized to form atoms. As expansion continued and temperatures fell, these particles joined to create hydrogen and helium, the universe's first elements. Hundreds of millions of years later, variations in density led gravity to collapse clouds of gas, initiating the formation of the first stars and galaxies. Over billions of years, galaxies interacted, stars were born and perished, and cosmic architecture grew more complex, shaping the vast universe we observe today. To better visualize this growth, imagine inflating a balloon with dots scattered on its surface. Each dot stands for a galaxy. As the balloon expands, the dots appear to move apart, not because they're moving on their own, but because the balloon's surface is stretching. This analogy mirrors how galaxies separate as space itself expands. Another metaphor involves rising raisin bread in an oven. As the dough swells, the raisins move apart, not because they're moving within the dough, but because the dough, representing space, is expanding around them. This cosmic expansion doesn't unfold within some pre-existing void. Instead, the growth of space itself is the defining characteristic of the Big Bang. Today, the Big Bang model is a cornerstone of contemporary cosmology, forming the basis for understanding how the universe has developed from its infancy to its present form. But many questions remain unresolved. What set off the Big Bang? What existed prior to this origin point, if anything? And what, if anything, lies beyond what we can currently observe? Further complicating the picture are discoveries from the late 20th and early 21st centuries involving dark matter and dark energy. These mysterious entities suggest our current knowledge is far from complete. Dark matter, which doesn't emit or interact with light, appears to bind galaxies together through its gravitational influence. Meanwhile, dark energy, a force that drives the acceleration of cosmic expansion, comprises most of the universe, yet remains largely unknown. These enigmatic elements push scientists to search for a more unified and fundamental understanding of the universe, perhaps one that goes beyond the Big Bang. In essence, the Big Bang concept offers one of the most remarkable scientific insights into the story of our beginnings. By examining the ongoing expansion of space and decoding the whisper of ancient cosmic radiation, researchers have reconstructed a timeline that leads back to a fiery birth. This theory reshapes our view of the cosmos, from a static stage to a vibrant, ever-evolving system with an origin, a present, and potentially a finale. While the Big Bang narrative answers some of humanity's most profound questions, it opens the door to even greater ones, questions that will guide the next generations in their quest to understand the truth of our cosmic roots. Blueprint of the subatomic universe. Picture the cosmos as a vast Lego universe, where everything you see, stars, planets, people, even the air, is built from miniature units, each with specific traits. The standard model of particle physics functions like a detailed instruction guide for these units, listing the fundamental pieces that compose all matter and the forces that connect them. But crafting this guidebook was anything but simple. It emerged through decades of revolutionary discoveries, ingenious thinking, and relentless scientific inquiry into the building blocks of reality. This monumental framework didn't materialize overnight, nor was it the work of a lone genius. Its roots trace back to the late 1800s and early 1900s, when researchers were unraveling the mysteries of atomic structure. In 1897, J. Thomson revealed the electron, disproving the notion that atoms were indivisible. This showed that atoms contained even smaller components. A few years later, in 1911, Ernest Rutherford conducted his gold foil experiment, revealing a dense atomic center, the nucleus, surrounded by electrons. These milestones launched an era of atomic research, showing that atoms themselves weren't the most basic forms of matter. Throughout the early 20th century, more subatomic entities came to light. By the 1930s, scientists had confirmed that protons and neutrons made up atomic nuclei. But new questions arose. Were these particles truly elementary, or did they consist of smaller constituents? And what invisible forces were keeping them bound? As research advanced, two major breakthroughs, quantum mechanics and Einstein's theory of special relativity, helped physicists understand behavior at extremely small scales and high velocities. In the 1950s and 60s, massive machines known as particle accelerators were built. These devices smashed particles at immense speeds, enabling scientists to observe phenomena previously hidden from view. Every new collision unearthed a new particle, pions, muons, and other exotic forms, which overwhelmed physicists with an explosion of discoveries. The influx of unfamiliar particles was so intense that it earned the nickname, the Particle Zoo. Amid this overwhelming catalog of subatomic entities, scientists searched for a unified explanation, a theory that could categorize these particles and describe their behaviors. That quest culminated in the development of the Standard Model, a powerful theoretical structure that combined three of the universe's four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. A major breakthrough came in 1964 when Murray Gell-Mann introduced the concept of quarks. Quarks are considered elementary particles that merge to create larger composite particles like protons, neutrons, and other hadrons. Similar to how letters join to form words, different combinations of quarks result in the various particles observed in nature. Initially, Gell-Mann proposed three types of quarks: up, down, and strange, which explained many of the previously detected particles. This renewed belief in a deeper layer of matter. Over time, scientists discovered there were actually 6 varieties, or flavors, of quarks: up, down, charm, strange, top, and bottom. These combine in multiple ways to construct matter as we know it. Quarks are held together by the strong nuclear force conveyed by particles known as gluons, which act as the binding agent within protons and neutrons. Beyond quarks, the Standard Model also identifies leptons, such as the electron, and bosons, which are particles responsible for force transmission. Each fundamental force is mediated by a unique boson. Photons govern electromagnetic interactions. W and Z bosons facilitate the weak nuclear force responsible for radioactive decay, and gluons transmit the strong force that keeps quarks together within atomic cores. Though these pieces steadily completed the puzzle of the Standard Model, one crucial question remained: mass. While the framework accurately described particles and their interactions, it didn't explain how mass arises. In 1964, Peter Higgs and other theorists introduced the idea of the Higgs field, an invisible field permeating the universe. As particles pass through this field, they interact with it and gain mass, similar to how an object moving through water experiences resistance and slows down compared to its movement through air. This theory predicted the existence of a new particle, the Higgs boson. For many years, the Higgs boson remained a hypothetical particle. The Standard Model demanded its presence, but no experiment could verify it until 2012. That year, scientists working with the Large Hadron Collider in Switzerland finally detected the elusive Higgs boson, providing crucial evidence that confirmed a central prediction of the model. To better understand the Standard Model, imagine a vast unseen framework connecting all things. This network consists of particles that interact by exchanging invisible messenger particles. For instance, think of two friends tossing a ball between them. The ball represents a force, like electromagnetism, and the act of throwing it simulates their interaction. Particles in nature toss messenger bosons, like photons or gluons, to engage with one another. Another helpful metaphor: think of quarks as ingredients with different flavors. Just as a sandwich can be made with a variety of components, particles such as protons and neutrons are made of different quark combinations, held together by gluons. This recipe of quarks, gluons, and force carriers is the foundation of everything in our universe. The Standard Model is astonishingly accurate. It has predicted countless particle behaviors, which have consistently been confirmed through experiments. Yet, it is not a complete theory. Gravity, the fourth fundamental force, is notably absent, and the model offers no explanation for dark matter and dark energy, mysterious components that dominate the cosmos in terms of mass and energy content. Other puzzles remain as well. Why are there exactly 6 quarks and 6 leptons? Why do particles have the specific masses that they do? Despite these open questions, the Standard Model stands as one of modern science's greatest accomplishments. It encapsulates our current understanding of the fundamental ingredients of reality and the forces that govern them. Like a finely crafted blueprint for the microscopic world, it connects the tiniest known particles with the grand structure of the universe. While it solves many age-old riddles, it also invites further exploration, challenging scientists to dig deeper, refine their theories, and discover what lies beyond the known in pursuit of a more complete picture of the cosmos. The fading shadows of black holes. Imagine colossal entities in space, cosmic predators consuming everything in their reach, even beams of light. For generations, black holes were seen as ultimate one-way voids. Once matter crossed their boundary, it vanished eternally. But in the early 1970s, a brilliant young physicist named Stephen Hawking revolutionized this belief with a startling proposition. Contrary to long-held assumptions, he suggested that black holes could actually emit radiation. And astonishingly, this process could eventually cause them to vanish entirely. This revolutionary phenomenon, now called Hawking radiation, dramatically altered our perception of black holes and introduced profound new mysteries about how the universe functions. To grasp how Hawking developed this idea, we must examine the scientific landscape of the 20th century, dominated by two foundational but seemingly conflicting theories: Einstein's general relativity and quantum mechanics. General relativity illustrates how massive objects distort the space-time fabric, producing gravitational effects. On the other hand, quantum theory explains how matter and energy behave at incredibly tiny scales. Black holes, however, exist at the critical crossroads of these two theories, where gravity becomes so overwhelming that quantum behaviors cannot be overlooked. At Cambridge University during the early 1970s, Hawking set out to examine black holes through the lens of both gravity and quantum physics. Until then, black holes were understood to grow larger by pulling in nearby energy and matter, nothing more. They were considered unchanging beyond their consumption. Yet quantum theory hinted at strange activity occurring near the event horizon, the invisible boundary beyond which nothing can return, not even light. Hawking's insights stemmed from the bizarre nature of quantum fluctuations, the idea that what we perceive as empty space is actually a restless sea of fleeting particles. In the quantum vacuum, pairs of particles and their corresponding antiparticles constantly form and annihilate each other almost instantly, leaving behind no observable trace. But Hawking proposed something extraordinary. When one of these pairs forms right at the edge of a black hole, it's possible that one particle may be captured by the black hole, while the other escapes into space. This escaping particle would appear to a distant observer as radiation emitted from the black hole. Thus, what had once been believed to be an inescapable region began to look like it could shine. This radiation became known as Hawking radiation. Hawking determined that this escaping energy would slowly drain mass from the black hole, leading to a gradual loss of mass, a phenomenon now referred to as black hole evaporation. If this process continued over immense spans of time, the black hole could theoretically shrink out of existence, ending in a final burst of energy. This idea upended the prevailing concept that black holes were eternal prisons. Instead, they were revealed to be impermanent, capable of fading away. Hawking's theory transformed the way scientists viewed black holes, not as cosmic dead ends, but as entities that could emit energy back into the universe. But Hawking's radiation didn't just challenge ideas about black holes, it opened a can of philosophical and scientific dilemmas, especially regarding information. In quantum mechanics, one key principle is that information about a system is never truly lost. It can always be theoretically recovered. But if black holes radiate energy and eventually vanish, what happens to the information about everything that fell inside them? This contradiction is known as the black hole information paradox. If that information is lost forever, quantum mechanics itself would be called into question. If it's somehow preserved, it suggests the presence of new physics that we do not yet understand. To this day, scientists continue to investigate this paradox, as it represents a key challenge in bridging quantum mechanics with general relativity. Imagine a thriving metropolis with a central waste facility that supposedly incinerates every piece of garbage completely. For years, it's believed nothing ever leaves this facility. But then, unexpectedly, researchers notice that under special conditions, some particles escape from its edge. Even more surprising, as more particles slip away, the facility itself begins to shrink, until one day, it simply ceases to exist. This analogy captures the essence of Hawking's insight, that black holes, once considered indestructible space vacuums, can slowly shed mass and vanish thanks to quantum processes. The revelation of black hole radiation propelled Stephen Hawking to worldwide fame, not only among physicists, but also among the general public. His work offered a rare glimpse into the quantum secrets of black holes and moved science closer to the ultimate goal of unifying the universe's most powerful principles, gravity and quantum mechanics. The quantum wonders of zero resistance today, what we call Hawking radiation, is recognized as one of the most profound theoretical insights of 20th century physics. It has driven countless investigations into the mysteries of black holes, quantum gravity, and the very structure of space-time. Yet detecting Hawking radiation directly is virtually unfeasible. The radiation is astonishingly weak, far dimmer than the cosmic microwave background lingering from the Big Bang. For the majority of black holes, this process of slowly radiating energy, known as evaporation, would take an amount of time vastly greater than the current lifespan of the universe. Still, researchers have developed Earth-based experiments to simulate key features of Hawking radiation through analog systems, such as manipulating sound waves in carefully chosen materials. These creative setups aim to shed light on how black holes might actually behave. Hawking radiation remains a milestone achievement in our comprehension of black holes. It shows that even the most enigmatic and remote entities in the cosmos can be understood. Stephen Hawking's revelation challenged the notion that black holes are eternal traps. Instead, he portrayed them as dynamic, interactive elements of the universe. Thanks to this discovery, our view of the universe grew sharper, paving the way for future revolutions in science as researchers continue to probe the astonishing depths of space, time, and the nature of reality itself. In the early part of the 20th century, as scientists delved into temperatures approaching absolute zero, that is, roughly minus 273.15 degrees Celsius or 0 Kelvin, they stumbled upon baffling properties in certain substances that defied the established rules of physics. Two of the most captivating phenomena to emerge from these frigid explorations were superconductivity and superfluidity. These rare effects occur only at extremely low temperatures and unveiled a new frontier in physics, continuing to spark advances in science and technology today. The story of superconductivity begins in 1911 when Dutch physicist Heike Kamerlingh Onnes, working at the University of Leiden, led the way in the science of cryogenics. In 1908, he became the first to successfully liquefy helium, achieving temperatures just a few degrees above absolute zero. This breakthrough enabled him to explore how materials behave in extreme cold. One of Onnes's key experiments focused on mercury, a metal already known to be a decent conductor of electricity at normal temperatures. But as he cooled mercury down near absolute zero, he observed something extraordinary. At 4.2 Kelvin, or about negative 268.95 degrees Celsius, the metal's electrical resistance, normally the culprit of energy loss as heat, suddenly vanished. Mercury began conducting electricity without any resistance at all. This was the first recorded discovery of superconductivity. To understand its importance, consider a common scenario. Typically, when electric current flows through a wire, some of the energy is lost as heat due to resistance. It's like water moving through a pipe with friction. Some energy disappears as it brushes against the walls. In contrast, a superconductor acts like a perfectly smooth pipe, letting electricity flow effortlessly and indefinitely without any energy loss. This zero-resistance behavior opens tremendous possibilities, including efficient electrical systems, powerful MRI machines, particle physics research, and magnetic levitation trains, maglevs. But the scientific mystery remained. Why does this happen? It took decades to answer. In 1957, American physicists John Bardeen, Leon Cooper, and Robert Schrieffer proposed the BCS theory to explain superconductivity. They suggested that under ultra-cold conditions, electrons in a superconductor pair up into what are called Cooper pairs. These pairs travel through the material in perfect synchrony. avoiding collisions that would usually cause resistance. This synchronized movement allows electrical current to flow without losing energy. Meanwhile, another bizarre phenomenon emerged: superfluidity. Unlike superconductivity, which occurs in solids, superfluidity was discovered in liquids. In the 1930s, Soviet physicist Pyotr Kapitsa and American scientists John Allen and Don Mizner noticed an unusual behavior in liquid helium. When cooled below 2.17 Kelvin, helium underwent a dramatic transformation. It began to flow with zero viscosity or resistance to motion. Kapitsa named this behavior superfluidity. Imagine stirring a glass of water, and instead of slowing down, the water spins endlessly. That's what happens in a superfluid. Superfluid helium can climb walls, seep through minuscule gaps, and circulate forever in a loop without any external force. This seemed to violate all known laws of fluid behavior, until quantum mechanics offered an explanation. The key was Bose-Einstein condensation. At extremely low temperatures, helium atoms stop behaving like individual particles and start acting as overlapping quantum waves, forming a unified, frictionless state. This harmonious movement allows superfluid helium to flow without any internal drag. The discoveries of superconductivity and superfluidity have left deep impacts on both science and industry. Superconductors enable the world's most powerful magnets, crucial in medical imaging, like MRIs, and particle colliders such as the Large Hadron Collider, which explores the tiniest building blocks of the universe. They are also foundational in the development of frictionless maglev trains, which could one day revolutionize transportation. While superfluidity is still primarily a subject of laboratory research, it has profoundly influenced our understanding of quantum mechanics and exotic forms of matter. Studies on superfluid helium have provided insight into quantum turbulence and sparked interest in even more curious states, like Bose-Einstein condensates in ultra-cold atomic gases. To visualize these phenomena, think of a regular liquid as a crowd of people walking down a hallway. Each person must dodge and adjust, resulting in a messy, slow movement. A superfluid, however, is like that same crowd suddenly dancing in perfect silent synchronization. No collisions, no slowing, just seamless motion. Similarly, imagine electrons in a normal wire as cars on a bumpy road, frequently slowed by traffic and curves, resistance. In a superconductor, those cars are paired up, cruising smoothly and endlessly on a flawless highway, never losing speed. These groundbreaking discoveries have opened a window into the bizarre world of quantum physics at near zero temperatures. They challenge our everyday expectations and expand our view of what matter can do. And as scientists push forward, especially in the quest for superconductors that work at higher temperatures, the promise grows for smarter energy systems, cutting-edge technologies, and deeper knowledge of the quantum universe. The universe designed for awareness, understanding the anthropic principle. The anthropic principle is a thought-provoking idea at the intersection of science and philosophy, aiming to unravel one of humanity's most fundamental questions. Why does the universe seem perfectly adjusted to support life? Derived from the word anthropic, meaning human, this principle asks why our universe possesses the specific physical characteristics that make it possible for sentient observers to emerge and contemplate it. Though early notions of this idea existed, it wasn't until the latter part of the 20th century that the anthropic principle was formalized and took center stage in cosmological and philosophical discussions. It has since influenced critical conversations in fields like quantum theory, cosmology, and the debate over multiple universes. The journey begins in the early 1900s when physicists were identifying the fundamental constants that govern nature, like the speed of light, gravitational force, and electron charge. Scientists observed that if any of these constants were just slightly altered, our universe wouldn't be capable of forming stars, creating atoms, or sustaining life. This observation led to the conclusion that our cosmos appears finely calibrated to allow life to exist, much like a finely composed melody where every tone is tuned with precision to create harmony. In the 1960s and 1970s, British cosmologist Brandon Carter played a key role in articulating this principle. He officially presented the idea in 1973 during a scientific event, honoring Nicholas Copernicus's 500th birthday. Carter argued that the physical laws and constants of the universe aren't arbitrary. Rather, they seem biophilic, meaning favorable to life. The anthropic principle is usually described in two main interpretations: the weak anthropic principle, WAP, and the strong anthropic principle, SAP. 1. Weak anthropic principle, WAP. The weak version suggests that the universe must have the properties required for life, simply because we are here to observe it. This means it's no surprise we see a life-permitting universe. If it didn't support life, we wouldn't be here to notice. Essentially, the WAP doesn't provide an explanation for why the universe has these traits. It just states that it has to, given our existence. It's often viewed as a self-evident truth, rather than a theory that uncovers deeper causes. 2. Strong anthropic principle, SAP. The strong interpretation pushes the idea further. It proposes that the universe isn't just accidentally suited for life, it's inherently structured in a way that must lead to conscious observers. This version implies that the universe might have a built-in purpose or intention, an idea that is controversial and widely debated. To grasp this better, imagine walking into a kitchen and discovering a cake baking with exactly the right mix of flour, sugar, eggs, and other ingredients. If any single component were off, the cake would fall apart or taste terrible. Naturally, you might ask, why are these ingredients so precisely measured? In the same vein, the anthropic principle posits that the universe has the exact recipe to allow life to arise. If it didn't, we wouldn't be here to ponder its properties. In the late 20th century, the anthropic principle gained momentum, especially as cosmologists explored the concept of a multiverse, the idea that an enormous or infinite number of universes may exist, each with different physical laws. Within this framework, the anthropic principle is used to explain why we happen to exist in a universe with life-supporting constants. We're in the one where life is possible, out of countless others. The principle also intersects with concepts in string theory and quantum physics. Certain interpretations of quantum mechanics suggest the universe only chooses a definite state when it is observed. This adds a new layer to the anthropic idea. The act of observation itself may help define the universe's reality. However, the anthropic principle isn't without criticism. Some scientists argue it doesn't meet the standards of scientific inquiry, since it doesn't generate testable or falsifiable predictions. Critics claim it functions more like a philosophical position, potentially sidestepping efforts to discover fundamental physical laws. Supporters, however, argue that the principle offers a useful perspective. It steers scientists away from seeking explanations for conditions that are, in fact, prerequisites for life. For instance, instead of endlessly probing why a certain physical constant has its exact value, one might acknowledge that if it were different, we wouldn't be here to question it. In recent years, the anthropic principle has fueled fresh scientific thinking. Physicist Leonard Susskind, a champion of the multiverse idea, has suggested that the anthropic principle might provide insight into the cosmological constant problem. This constant, which influences how quickly the universe expands, appears extraordinarily well calibrated to allow galaxies and life to emerge. Susskind and others believe that combining the multiverse concept with the anthropic principle may help explain why the constant is exactly what it is. The late Stephen Hawking also engaged with the idea, although with caution. He acknowledged that the anthropic principle offered a framework for understanding why the universe supports life. but he preferred explanations that were rooted in mathematical precision and physical models, rather than ideas suggesting cosmic purpose. Ultimately, the anthropic principle remains a powerful and provocative notion in modern thought. By examining the specific conditions required for life, it prompts us to reconsider our place in the grand scheme of the universe and whether there's a deeper rationale behind those conditions. Whether viewed as a logical necessity, a philosophical tool, or a hint of a greater pattern, the anthropic principle pushes us to wonder, is the universe simply life permitting by chance or by design? One thing is certain, it reminds us that the cosmos, with all its elegant laws and constants, is not just knowable, but also deeply mysterious. And perhaps, just perhaps, it was meant to be seen, questioned, and explored. Vibrations of the Cosmos, a journey through string theory. String theory aims to bridge two of the most foundational yet incompatible theories in modern science, quantum mechanics and general relativity. At its core, string theory proposes that the universe's most elementary components are not tiny particles like electrons or quarks, but instead microscopic vibrating filaments, strings. Each of these strings oscillates in a unique way, and its pattern of vibration determines the type of particle it becomes. Imagine the universe as a grand symphony, where each vibrating string plays a different tone, collectively composing the fabric of reality. Interestingly, string theory was not originally conceived as a path to unifying physics. Its roots date back to the 1960s, during a period when scientists were attempting to make sense of interactions inside atomic nuclei. At that time, researchers observed unusual behaviors among particles known as hadrons, a group including protons and neutrons, that couldn't be fully explained by existing models. Italian physicist Gabriele Veneziano discovered a mathematical expression, later dubbed the Veneziano amplitude, which surprisingly modeled these interactions with great accuracy. Scientists didn't immediately understand why the equation worked. They simply saw that it did. In 1970, physicists Leonard Susskind, Holger Beck Nielsen, and Yoichiro Nambu realized that Veneziano's equation could be interpreted as describing a one-dimensional string in motion. This marked a significant conceptual shift. Instead of treating particles as point-like with no size, they were now envisioned as tiny loops or strands that could vibrate in diverse patterns. Each unique oscillation corresponds to a distinct particle, much like how different plucks on a guitar string produce different notes. As researchers delved deeper, they uncovered that string theory offered a compelling framework to potentially unify all fundamental forces in physics. Yet early iterations of the theory came with peculiar predictions, including the need for 10 dimensions of space-time, far more than the familiar four we perceive, 3 of space, 1 of time. This initially seemed implausible, but theorists later proposed that these extra dimensions might be compactified, or curled up so tightly that they're undetectable in everyday experience. In the 1980s, a more advanced version called superstring theory emerged. This updated theory introduced the concept of supersymmetry, a theoretical balance between particles that carry forces, like photons, and those that make up matter, like electrons. Supersymmetry helped stabilize the theory's equations and allowed for more internally consistent mathematical structures. Superstring theory offered a bold vision, the unification of all four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, within a single theoretical framework. For the first time, physicists saw in string theory a viable contender for the long-sought theory of everything. To better understand this, picture a musical instrument like a guitar. Each string can vibrate at various frequencies, producing different notes. In the same way, the strings in this theory can vibrate differently, giving rise to the universe's various particles. One mode of vibration might appear as an electron, another as a photon. Just as a musician plays different notes by adjusting the strings, the
universe plays these fundamental vibrations to create matter and force. During the mid-1980s, however, researchers faced a new dilemma. Instead of one cohesive string theory, they discovered 5 different versions, each with its own unique equations and structures. This was discouraging, as scientists were striving for a single, unified model of everything. Then in the 1990s, theoretical physicist Edward Witten introduced a groundbreaking idea. He suggested that these 5 distinct versions could actually be aspects of a deeper, more comprehensive theory. He called this the M theory, which added yet another spatial dimension, bringing the total to 11. Within this framework, not only strings but also higher dimensional objects called brains, short for membranes, could exist. These brains could stretch across different dimensions and opened up fresh ways to think about reality. One of the most fascinating possibilities was that our entire universe could be a 3-dimensional brain existing within a higher dimensional space. If true, then parallel universes, other brains, might exist nearby, entirely separate but possibly interacting with our own. This bold idea contributed significantly to the development of multiverse theories.
Though string theory is elegant in its mathematics and rich in its conceptual possibilities, it remains largely theoretical. One of the primary criticisms is that it hasn't yet produced testable predictions that could confirm or falsify it through experiments. Some scientists argue this lack of empirical evidence puts it outside the realm of traditional science. However, advocates highlight that string theory has already yielded important insights, especially concerning black hole entropy, the early universe, and the structure of space-time. Despite its challenges, string theory continues to be one of the most promising candidates for a complete theory of the cosmos, encouraging physicists to explore bold new mathematical frontiers. It has even reached beyond physics into areas like pure mathematics, influencing the tools and methods used across disciplines. String theory stands as a testament to humanity's unyielding desire to comprehend the deepest truths of existence. It stretches the boundaries of our understanding of matter, space, and time, proposing that the universe may be made not of point-like particles, but of minuscule, resonating threads. Although experimental confirmation may still be far off, string theory lights the way forward, an intellectual journey not unlike that of ancient explorers sailing into the unknown. With each mathematical breakthrough, string theorists map new territories of reality, propelled by the hope that one day we may finally grasp the true nature of everything. Echoes from the Dawn, the story of cosmic microwave background radiation. The revelation of cosmic microwave background, CMB radiation, stands as a milestone in cosmic science, deeply enriching our grasp of the universe. This faint energy offers a direct glimpse into the early cosmos, taking us back nearly 14 billion years to moments just after the Big Bang. The path to uncovering this subtle remnant of the universe's youth began not in grand observatories, but in an unassuming site in New Jersey, entwined with theories developed years earlier. To grasp what CMB radiation truly is, envision the state of the cosmos shortly after its explosive origin. Roughly 380,000 years following the Big Bang, the universe resembled a searing, densely packed cloud of charged particles, a glowing plasma filled with photons, protons, and electrons. In that era, photons were continuously deflected by free particles, preventing them from traveling freely through space. Eventually, as cosmic expansion continued, temperatures dropped enough for protons and electrons to merge and form neutral hydrogen atoms. This transformation allowed photons to move without constant scattering, releasing a flood of light across the universe. This pivotal event is known as the Epoch of Recombination, and the light from that era has been journeying across space ever since. Over the course of billions of years, these photons had their wavelengths stretched by the expanding universe, shifting into the microwave portion of the electromagnetic spectrum. This stretch created what we now identify as the CMB radiation. Even before this radiation was physically detected, it was theoretically predicted. In the 1940s, physicist George Gamow, along with Ralph Alpher and Robert Herman, explored the consequences of the Big Bang model. They concluded that if the universe had indeed started in a hot, dense condition, there must still be lingering radiation from that initial phase. Their calculations suggested that, by now, this leftover energy should have cooled to just a few degrees above absolute zero, diffused throughout space. Despite this prediction, no immediate attempt was made to detect the radiation. It wasn't until 2 decades later, in the early 1960s, that two radio astronomers, Arno Penzias and Robert Wilson, stumbled upon it unintentionally. Working at Bell Labs in New Jersey, they were using a large horn-shaped antenna to pick up weak radio signals for satellite communications. Unexpectedly, the device began receiving a persistent, low-level hiss that appeared to originate from every point in the sky. Baffled, Penzias and Wilson suspected that the interference was technical in nature or possibly the result of urban noise. They even cleaned pigeon droppings from the antenna to rule out contamination, yet the mysterious hum remained, unchanged by direction, time of day, or season. Around the same time, physicist Robert Dicke and his team at Princeton University were actively searching for the very radiation predicted decades earlier. When Penzias and Wilson learned of this research and contacted Dicke, he immediately realized the importance of their accidental find. In response, he famously remarked, "Well, boys, we've been scooped." The signal Penzias and Wilson had encountered was exactly the remnant radiation predicted by Gamow, Alpher, and Herman, the cooled, stretched echo of the Big Bang. This was a transformative moment in astrophysics, marking the first direct observational confirmation of the Big Bang model. Following this landmark discovery, the scientific community intensified its efforts to study the CMB in detail. In the 1990s, NASA launched the COBE Cosmic Background Explorer satellite, which not only validated Penzias and Wilson's observations with greater precision, but also detected tiny variations in CMB temperature across the sky. These subtle differences mirrored the initial density fluctuations in the early universe, irregularities that would later evolve into galaxies, stars, and planetary systems. These minute shifts served as a cosmic snapshot, offering insight into the earliest formation of large-scale structure. Building on COBE's success, further missions like the Wilkinson Microwave Anisotropy Probe, MAP, and the Planck satellite delivered even more refined CMB maps. These observations enabled researchers to calculate the age, geometry, and composition of the universe with extraordinary accuracy. The CMB has become a kind of cosmic fingerprint, embedding crucial details about the universe's origins, matter content, and potential fate. Think of it as a distant echo in a canyon, a whisper from the universe's youth that resonates through time. Just like an echo reveals characteristics of the initial sound and its environment, the CMB conveys essential information about the universe's early conditions, softened, stretched, and cooled over billions of years of cosmic expansion. This radiation pervades the entire cosmos, forming a background glow, a faint but persistent afterimage of creation that helps illuminate the beginnings of all existence. The confirmation of CMB radiation changed the field of cosmology, enabling scientists to move from speculative theorizing to a measurable, empirically supported model of the early universe. In recognition of their monumental discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. What began as an unintended detection turned into one of the greatest scientific breakthroughs of the 20th century. Even today, investigations of the CMB continue, with researchers using it to probe profound mysteries such as dark matter, dark energy, and the fabric of the universe itself. What once appeared as inexplicable static in a radio antenna is now considered one of the cornerstones of modern cosmology, redefining how we understand the origins, evolution, and future of our universe. Unseen forces, the enigma of dark matter and dark energy. The revelation of dark matter and dark energy marks one of the most captivating and puzzling frontiers in today's scientific exploration. These two intangible components are thought to make up roughly 95% of the cosmos, yet they escape direct observation. We know of their presence not by visual evidence, but because of the unusual, unexplained effects they have on the observable universe. Their discovery is a tale woven from inquisitiveness, mathematical anomalies, and the unwavering resolve of researchers who noticed that the cosmos wasn't behaving as it should. The hunt for dark matter commenced in the 1930s, when Fritz Zwicky, a Swiss astronomer, studied the Coma Cluster, a gravitationally bound group of galaxies. Zwicky observed something odd. These galaxies were moving significantly faster than they should, given the amount of mass that could be seen. By Newtonian physics, such high speeds should have torn the cluster apart, but it held together. Zwicky proposed the existence of some invisible substance exerting gravitational force. He introduced the term dunkel Materiae, or dark matter, to describe this hidden mass that seemed to hold galaxies intact. Although his idea was ahead of its time, it didn't gain much traction until the 1970s, when new evidence breathed life into the theory. That evidence came through the work of American astronomer Vera Rubin, who analyzed how stars rotate around the centers of galaxies. According to physics, stars farther from the center should move more slowly, like how the outer planets revolve around the sun more gradually. Yet Rubin found that stars throughout galaxies were rotating at nearly uniform speeds, no matter their distance from the center. This unexpected motion suggested galaxies contained far more mass than what was visible. Stars, gas, or dust alone couldn't account for it. Just like Zwicky before her, Rubin concluded that an immense quantity of hidden matter must be generating the gravitational pull necessary to produce these motion patterns. Her research provided compelling support for the existence of dark matter and helped elevate the concept from a fringe theory to a central pillar in astrophysics. While dark matter helps explain unseen mass that binds galaxies, dark energy tackles a completely different mystery: the rapid acceleration of the universe's expansion. To explore this, we leap forward to the 1990s, when two independent research groups, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, set out to measure the pace of the universe's growth. At the time, it was expected that the expansion initiated by the Big Bang would be gradually slowing down due to gravitational attraction. Galaxies pulling on one another should eventually lead to a deceleration in the stretching of space. To test this theory, both teams turned to type Guia supernovae, powerful stellar explosions that shine with predictable brightness, acting as standard candles for measuring astronomical distances. To everyone's surprise, their findings contradicted expectations. Instead of decelerating, the universe was found to be speeding up in its expansion. It was as though an invisible repelling force was driving galaxies apart faster over time. This force was named dark energy, an unknown cosmic pressure that acts in opposition to gravity, pushing galaxies farther and farther apart across the expanding fabric of the universe. Think of the universe like a stage performance. The lights, actors, and scenery, what we can see, represent stars, galaxies, and visible matter. But every successful play has a backstage crew, stagehands, lighting techs, and directors who guide the show from behind the curtains. Dark matter is like that hidden crew, shifting the scenery and keeping everything structurally sound. Dark energy, in contrast, is the unseen director, altering the tempo of the performance, making the play unfold faster and faster as time passes. In this metaphor, dark matter keeps cosmic structures bound together, while dark energy stretches the very stage of the universe, increasing the distance between galaxies as if pulling the curtain wider and wider. Today, these two phenomena remain among the most profound mysteries in astrophysics. Dark matter appears to interact only through gravity, forming the scaffolding around which galaxies and clusters form. Despite decades of research, from deep underground particle detectors to high-energy collisions at the Large Hadron Collider, scientists have yet to directly identify a dark matter particle. Current hypotheses propose that dark matter may be composed of exotic entities like WIMPs, weakly interacting massive particles, or axions, but without conclusive detection, these ideas remain theoretical. Dark energy is even harder to grasp. Though its exact nature is unknown, one theory links it to the cosmological constant, a term Albert Einstein originally inserted into his equations of general relativity to maintain a static universe. Ironically, after learning the universe was expanding, Einstein discarded the constant, calling it his greatest mistake. Yet now, the cosmological constant has returned as a possible explanation for the repulsive force of dark energy. Understanding these invisible forces is critical. They influence the formation of galaxies, the geometry of the universe, and potentially its ultimate fate. Dark matter explains why galaxies cluster and behave as they do. Dark energy may determine whether the universe will expand forever, collapse, or reach a steady state. Some theories even suggest a scenario called the Big Rip, where expansion becomes so extreme that galaxies, and eventually atoms, are torn apart. Despite all efforts, much about dark matter and dark energy remains unknown. Yet the search continues, aided by advanced tools like the James Webb Space Telescope and surveys such as the Dark Energy Survey, which aim to map cosmic structures with increasing clarity. These instruments help scientists trace gravitational effects and subtle patterns in space that may reveal the secrets of these unseen forces. In the end, dark matter and dark energy remind us of the limits of our knowledge. They highlight how much of the universe remains hidden, urging the scientific community to probe deeper and ask more fundamental questions. Though they are invisible to our eyes, their influence is written across the stars, binding galaxies, shaping cosmic architecture, and propelling the universe itself. The quest to decipher their true nature lies at the very core of modern cosmology.